welcome everyone. So I'll be explaining two problems of DIV3 702 Codeforces round 702 DIV3, problem C and problem D. So in this problem we are actually we're going to be given one integer which the constraint is up to 10 to the power 12, and we have to return yes or no, and the condition is whether we can make this number as the sum of two cubic numbers. And also they have also we need to notice one thing here is that those two cubic numbers addition and those two cubic numbers, okay, A and B, following this condition, these numbers need to be positive, which means this condition, if for any integer, given integer x, if this condition occurs, a cubed plus b cubed equal to x for any integer x, if I get any two numbers, positive integers, such that their cubic additional result is equal to x, then the answer is yes, otherwise no. So we actually have to somehow get this, somehow need to identify whether we can make that number the addition of two cubic numbers or not. So if you slightly analyze it, you can see this constraint is going to help us a lot. Here the given number that we're going to be taking from the user, okay, this number is up to 10 to the power 12, okay, and let's say our x is up to 10 to the power 12. Now what does that actually mean? That means that if x, we have to fulfill this condition, right? A cubed plus b cubed. So we will try to find out whether which is the integer that is responsible for making this as in cubic form. If I say, okay, if this is the largest integer possible, 10 to the power 12, then we can easily say that these numbers, if I do cubic root, okay, 10 to the power 12, it will give us 10 to the power 4, which means we only have to consider numbers from 1 to 10 to the power 4. And what I did was I will initialize I will run out a for loop, and from 1 to 10 to the power 4, and indicating with a map value, key value, that this number's cubic value is exists, and it will be equal to 1, something like that. Okay, look, for this value from 1 to 10 to the power 4, let's call this value as val. What I actually did was, okay, I will initially, before taking any kind of test case, what I did was I took a map of value times value times value, right? I don't need to traverse all the way up to 10 to the power 12. I can do that up to 10 to the power 4, and then I can track it like this. Okay, I hope you get that. So from this operation that I'm going to be doing is before taking my test case. Now, how is this going to help us? After that, the task is pretty easy. What I have to do is I will only traverse, then let's say I have initialized all these cubic numbers as my map up to 10 to the power 4, and then I'm going to be taking x after taking the test case. What I have to consider is, let's say I took t and then x, okay, And what I have to do is, I actually don't need to um, traverse all the way up to x. What I can do, I can only, so my for loop will run only up to cubic root of x. Now why is that? That's obvious, because one of the values, if x is equal to a cube plus b cube, if I want this condition to be successful, then at least one of these values, one of these a and one of these b, will definitely be less than or equal to this cubic root of x. So if I somehow find a particular integer a such that I can calculate a cube, and then what I will do is I will try to find out whether, remember, we're only traversing for this a, okay, I equal to 1 up to cubic root of x, and trying to figure out whether this does exist in my map value or not. Now, what is actually this x minus a cube? This is nothing but b cube. So I'll try to find out, if I assume that this is my a, then I will try to find out a cube, x minus a cube, which is nothing but b cube, and I will try to find out whether this b cube actually exists in my map or not. If it does exist, I'm gonna be just breaking it. So that's it. I'll take you to the code part. The code part is actually, okay, this is the code part. What I actually did was, look, exactly what I told you. I'll try to initialize each and every values up to 10 to the power 4. These values, cubic numbers, as map value equal to 1. Just tracking out. And then just checking out whether they exist or not, and just indicating that they exist, and taking x and my a. This is just assume that this I refers to a, and this a will be up to cubic root of x. Look, this line exactly means like this: I less than or equal to cubic root cubic sqrt of x. Okay, so if I do just cubic root, I am exactly doing the same thing here. Normally when we do I square or sqrt of x, if I do this, it's actually the same thing if I say it like this, because I'll show you here, you'll understand better. Saying the same thing like I square, or let's say I cube less than or equal to x, is actually the same as I less than or equal to. So instead of going for this, I just went for this. That's it, nothing else. Okay, so I cube less than or equal to x is equal to I less than or equal to cubic root of x. So that's exactly what I did here, and this is for my value b. Okay, this is for b. And if I say b cube, actually this is for b cube, and then I'm checking whether my b cube does exist or not. If it does exist, okay, I'm just breaking it, and if breaking it and tracking that yes, I have found out a positive result. If I found out, it's yes, otherwise no. Hope I made you understand. Now let's jump into the problem D. Now this problem is actually pretty easy if you understand the statement well. It's actually just saying you that you're going to be given a permutation, and you just have to make a tree. How this tree is going to be built, let me show you with an example. And finally, well, when you somehow make that tree, you have to, according to the rules said by this statement, after that you just have to print the depth of each and every node that of this tree. Okay, according to this ID. Now, how actually you're going to be building this tree? Let's take this example: 1 3 2 7 5 6 4. What I said, you're going to be given a permutation. You have to build a tree after according to the rules above they say it about in the statements, and after that you just have to print the depth of each and every node that you're going to be building of the permutation actually, which is actually a tree. Now, what was the example? 1 3 2 7 5 6 4. 1 1 3 2 7 5 6 and 4, right? Clarify this. Okay, yes. So what you have to do is, this is your permutation, your n is 7. Now what they've said that, okay, your permutation's root value, root node, is the maximum out of this array, from this array. So what is the maximum amongst all of these 7 value? It's 7. Okay, this is my root, and then what I have to do is, for the left subtree, the same rule follows, but for the group which are left of the maximum that I've already measured. Now, what is the maximum yet that I've counted? I've got, it's 7. Now, what is left of the 7? All of these values will be the part of the left subtree, and the right part will be for the right subtree. And remember what I said, this part is actually gonna work. You could imagine as a the same thing that we're doing here. What we have to do to measure this node, you have to find the maximum amongst what? This portion, because I already said left subtree belongs from the maximum values where it is actually lying on that array. Its leftmost, all values will be considered on the left subtree, and the rightmost one will be considered in the right subtree. And for the let's say we're going to be dealing with the leftmost one. Now what I have to do is I have to find for the leftmost. Now we're considering that this is one part here. Now we're only just trying to get the attention of these left subtree. Now for the left subtree, what is the maximum? It's 3, right? Okay, now so I'm just putting here for the left subtree, the maximum is this. Now for this value, I have what? I have got for this maximum value, its left subtree portion and area is this, and its right subtree portion and area is this. So it's going to be like 1, maximum out of this, and maximum out of this is 2. Similarly, right here, I'm going to be building like that. It's going to be 6, because in the rightmost area, what is the maximum? 6. Now for this 6, what is the leftmost area? This. What is the rightmost area? This. Maximum. Each time maximum. Okay, that's exactly how you're going to be dealing with this problem. Okay, just like that. Again, if I take another example, just to make you clarify one more time: 3 5 2 1 4. 3 5 3 5 2 1 and 4. Yes. Yeah. So how we're going to be dealing? initially the root will be the maximum. Okay, what is the maximum? It's 5. Now it is divided into two parts, the leftmost and the rightmost. The leftmost will be the member of the leftmost subtree, and here there is only one value, so it doesn't matter whether whether it's big or small. Now for the rightmost, okay, now the bigger one counts. The node will be what? The maximum out of those rightmost area. What is the maximum? It's 4. Now if this is filled, it has a leftmost area here, rightmost there is no one. So out of these two values, what is the maximum? It's 2, definitely. If this is covered, what is left for this value? Leftmost is already fulfilled, but the rightmost is also left. Only one value will be here. Now, what you have to do, finally what you have to do is you have to print each and every node's depth. Now, how would you calculate the depth? They actually gave a description about how you would calculate the depth. I will also tell you, what you have to do is you have to count how many edges from the root of that node. Now, if I say from 3, what is the depth of node 3? What is the root? The root is 5. So from root till this node 3, how many edges are available in the longest path, in the path? Okay, from 5 to 3, there are only one edges, which is the so the depth will be 1 for node 3. What about node 5? It's going to be 0 for real, because from 5 there's no edges here, so its depth will be 0. For 4, it's going to be 1. What about for 2? It's going to be, okay, there are 2 edges. From 5 to 2, there are 2 edges. We can count. It's going to be 2. And from 5 to 1, how many edges are there? 1, 2, 3. Okay. So what you have to print is this. Okay, this depth. Now this problem, it's pretty easy if you know recursion well. What you have to do is a simple divide and conquer problem, conquer solution. Okay, how is this works is simply because if you look at the constraints here, n is very small. Okay, n is very small. It's 100. You just calculate divide and conquer like this. What you have to do? How did I measure the divide and conquer algorithm? Let me clarify this. I actually called a function, let's say solve. Inside that solve function, I'm delivering 1, n, and 0. Why is this for? This is actually for the initial array where there are all elements available. And for the initial array, what will be the leftmost value? It's going to be 1, and the rightmost will be n. And for the root value, what will be the height or depth? It will be 0. Okay. So what I did was, I simply, let's say I have this, and this. Okay. What I did was, let's look. If I say solve function of 1 to n, from now I am here inside my root, and I will make 2 categories of solve function. One will go from the what? Okay, let me tell you the process. First, what we're going to be doing inside that solve function initial, what we're going to be doing, we're going to be finding out the maximum of these two ranges. Let's initialize and generalize it as L and R. Okay, let's see. Generalize it as L and R. So solve L, R, and H. H means the depth. Okay, and this is R. Okay, so this function, inside this function, what we are going to be doing, trying to find out the maximum out of these 2 ranges, also the position of that maximum value. So I will find out max and the position. When I find this position and max, then I will just do two transitions. They will look simply like this. One will be from left to position -1 and age +1, simply because I'm going down. If I'm going down, the depth will definitely increase, because one edge, I am actually adding one edge, so definitely one depth will increase. And what will be the other transitions? It will be position +1 comma R and H +1. So this is going to be the two transitions, because I'm going to be creating a binary tree. They've already told that. They also told that actually the tree that we're going to be building is binary tree. So definitely there are going to be two transitions, leftmost for this and rightmost for this. And when I'm going to be doing this transition, and when I'm going to be actually finding out the maximum and the position, I will initialize my answer as this. Like, my answer will be answer of this value, which is maximum value, equal to the age. Okay, when I go and when I try to do that task before the transition. Okay, so that's how you're going to be doing the divide and convert. Okay, so what will be the base case? The base case will be when L equal to R. There's nothing we can do about it. If L is equal to R, we know what is going to be the result. The result is going to be the maximum is going to be the value itself, and we're going to be returning from that. And yeah, that's how you're going to be doing. I hope I made you understand. Let's take you to the code part. You'll understand more. So this is the divide and conquer portion. So what I did was taking the test case here and taking n and taking those values and values, and this is for the root value, starting from the root value. So L will be 1 and R will be n and our depth will be 0. Okay, this is the final array. What I said was the depth that I will insert inside this value for each value inside this tracking value. Okay, this is for the depth one, the depth value, which is going to be returning here. So the fun part is inside the solve function. Here we go, and this is the base case that I told you. When L equal R, we know what is the maximum one. That's why I'm actually initializing this, assigning this value inside this, assigning the what? The depth, because we need to find depth. Now inside this, what I said that before the transition, before the two transitions that I'm going to be making, what I have to do, I have to find out the maximum out of these L and R, between these L and R inclusive, and also the position. When I find out the position and all of this, and I'm going to be initializing of maximum, which means the answer of maximum equal to h, because yet I have found out that yes, I have covered up edges, and just initializing here. After that, I'll be making two transitions, because if I found out this node, I know I have to go from left transition and right transition, because I have to create binary tree. And if I have to create binary tree, I have to do two transitions, one to the left, one to the right. From what? From the position of what? The maximum value. So the maximum values positions, from the maximum values positions, I will go to the left and to the right. How it's going to be happening? Like this. Now, what is this if statement doing here? This if statement is actually considering one key fact, because if position -1 somehow, this is actually referring if my maximum values position is actually, if somehow it becomes equal to L, or if somehow my position, maximum values position, becomes equal to R, what will we do? We don't have to transition on that on that period anymore. That's why we're making this if value. This if condition is executing here. Okay, so that's how we're going to be doing. After that, we're going to be just returning that from here. Hoping you understand that. Till next time, goodbye.